So the next topic that we're going to be discussing here is angular momentum. The symbol for angular momentum is going to be the capital L. Okay? So let's reference the equation for linear momentum. Linear momentum, lowercase p, equals mass times velocity. So what do we think angular momentum is going to be? It's going to be rotational inertia times angular velocity. Right? Makes sense. So one important thing to know when we're dealing with angular momentum is a relationship that is not given on your reference table, and that is that linear velocity v equals angular velocity times radius, okay? So what exactly does that mean? It means that if we're dealing with circular motion and we have a particle moving in a circular path, that means the linear velocity at a particular instant is equal to that particle's angular velocity times its radius from the axis of rotation. So that is an important relationship to realize because it is analogous to all the rotational quantities. If v equals omega times r, it means x equals theta times r, and a equals alpha times r. You'll see why this is important when we start to look at problems or practice problems regarding conservation of linear momentum. All right, sorry about that. It is getting really hot in here. I have to take the good old jacket off. Okay, so we were talking about angular momentum and conservation of angular momentum. So again, the main reason why a lot of kids regard the the rotational unit as the hardest unit is because we are literally taking every unit prior to this and then just applying it to rotation. It's literally all 5 or 6 units all over again. Conservation of angular momentum, same deal as before. Your angular momentum at the beginning has to equal your angular momentum at the end. So the best way that we can explain angular momentum and conservation of angular momentum is through a practice problem. And the best way to illustrate that is as follows, okay? We have a center of rotation denoted by that dot. We have a small wooden board or wooden stick that extends with radius r away from that center of rotation. We're going to be given that the moment of inertia of this rod about that radius of about that center of rotation is equivalent to 1 over 12 the mass of the rod times the radius of rotation squared. We're going to say that the mass of the rod is m. Okay, and we're also given that we have a particle, that particle having mass 4m and speed 10 meters per second, okay? The problem is going to tell us that this ball collides with the rod and the two stick together. And after that, they want you to determine the angular velocity of the system, of the rod as it rotates around the center of rotation. Now, to be clear, this apparatus is done on a table, okay, a frictionless table, meaning the ball is rolling around the table with zero friction, and the center of rotation is perpendicular to the table going up and down, meaning the axis of rotation is up and down, and the plane that we are rotating in is the flat plane on the table. The importance of that is that the force of gravity is pointing downwards into the table along the axis of rotation, and we are not going to need to consider that. We have our givens, and we are looking for the angular velocity of the system, the final angular velocity of the system. So we're going to use law of conservation of angular momentum. Well, how can we do that? I have one thing that has linear momentum and one thing that has angular momentum. What am I to do? Well, we are going to consider the scenario the moment before the collision occurs. Okay? So the moment before the collision occurs, my particle is at radius r from the center, and it has the same mass, same velocity. However, the moment before it collides with the rod, we can convert the particle's linear velocity to angular velocity. We can say that the particle's linear velocity v equals the particle's angular velocity omega times its radius. Okay, we're going to say 10 linear velocity equals the particle's angular velocity times radius. Therefore, the moment before it collides with the rod, the angular velocity of the particle equals 10 over r. Okay? And now that we have an angular velocity for the particle, we can now use that angular velocity to plug into angular momentum. We're given angular momentum equals moment of inertia times omega. But wait a minute. I am given a mass for the particle. I'm not given a moment of inertia. But if we come back here, we can look at this and understand that this is type B. Type B being that we have a particle that is moving some distance r away from the axis of rotation. We have a particle that at a moment before collision will be right here, some distance r away from the axis of rotation. Therefore, we're given that the moment of inertia for this particle at that instant is going to be the mass of the particle times the radius of rotation squared, which in this case would be 4m r squared. Therefore, the angular momentum of the particle just before the collision is equal to 4m r squared times omega 10 over r, or 40 mr, because these cancel. So that is our initial angular momentum for the particle, which is our total angular momentum. Because the moment before the two collide, the rod is not moving. Okay? We're given that the two stick together after they collide, therefore is a perfectly inelastic collision. Therefore, angular velocity of the particle equals angular velocity of the rod after the collision. Okay? And in the same way how in linear analysis, if two masses collide, the total mass is now the sum of the two masses. In rotational physics, if two objects collide, the new moment of inertia is the sum of the individual ones. So now our new moment of inertia is the moment of inertia of the rod, 1/12, times the mass of the rod times r squared, plus the moment of inertia of the particle, which would be 4m r squared. 49 over 12 mr squared is our new moment of inertia for the whole system. Okay? Moment of inertia of the rod plus moment of inertia of the particle. So now I'm going to exhibit the initial angular momentum, and I'm going to set that equal to final angular momentum. Initial angular momentum being 40 mr, final angular momentum being 49 over 12 mr squared multiplied by our angular velocity, omega system. Okay? So, again, this is just a simple equation now that we need to solve. 40 mr, our total angular momentum, equals the moment of inertia of the two participant system, which is 49 over 12 mr squared, times the angular velocity of the system. So now let's solve for angular velocity. Okay? We've got mr on both sides of the equation. So now we can rewrite this as 40 equals 49 over 12 times r times the angular velocity. We can say that 40 times 12 over 49 equals the radius times the angular velocity. If I grab my calculator, 40 times 12 divided by 49 equals about 9.8, equals the radius of rotation times the angular velocity of the system. So now we can say the final angular velocity of the system equals 9.8 over our radius of rotation. So we found our angular velocity right there. And that is how we apply conservation of angular momentum plus this linear rotational equivalence. Okay? Let's see. What unit haven't we covered yet? Energy. Let's move on to that. All right. So before we move on to energy, I'm sorry, there's one more thing we need to cover in the domain of angular momentum. Okay? And that is the rotational analog of the impulse momentum theorem. That is that the change in angular momentum equals... So let's reference the impulse momentum theorem from linear. Change in linear momentum equals force times change in time. Okay? So the rotational analog of momentum is angular momentum. What's the rotational analog of force? Torque. And time is time everywhere. There is no rotational analog for it. Times change in time. That being the impulse momentum theorem in rotational form, okay? Effectively stating that the increase or decrease in angular momentum is equivalent to the torque applied to the rotating body times time. Now, just like linear momentum, angular momentum is a vector. It can be clockwise or counterclockwise. Torque is a vector. It can be clockwise or counterclockwise. So if I have a rotating body that is rotating clockwise, that's counterclockwise, and I say that it's rotating around a solid stationary rod, and there is friction between the rotating disc and the central rod, you would say that the friction is opposing the motion of the disc, okay? So since friction always opposes the motion of an object, we would say that since the frictional force is applying a force, and that force is at some distance away from the center of rotation. Since it's a thin rod, it's a very small distance, but it's a distance nonetheless. We can say that the frictional force exerts a torque on this rotating disc. And since the this torque exerted by the frictional force is in the opposite direction as the direction of rotation, we can say that this torque is slowing down the rotation. The torque is being applied in opposition to velocity. Therefore, the torque is reducing our angular momentum L, because the momentum vector and the torque vector are opposing. And as we can also see here, the period of time over which that frictional torque is being applied also has an effect on the change in angular momentum. Now, as we remember, frictional force acts opposed. We can increase angular momentum by applying a torque in the same direction as velocity, like giving it a little push in that direction. That's going to increase our angular momentum. Okay, now we can move on to rotational energy. Let's see if we can reason our way through the rotational energy equation. The kinetic energy of a rotating body is analogous to the kinetic energy of a linear body. So let's derive this out. Kinetic energy for rotation equals 1/2 times inertia. Linear inertia is mass, rotational inertia is I, times linear velocity is v, rotational velocity is omega. Oh, look how easy that was. The best way to understand kinetic energy here in this case would be looking at an example. So let's do that. This is an example that was on one of my tests in physics E mechanics, but it serves to illustrate this principle very, very well. Let's say you have a wheel here, okay? And wrapped around the wheel is a very long piece of string, wrapped around continuously, okay? And that piece of string is allowed to hang off the edge, and it's connected to a block of mass m. Okay, you're given that this wheel has moment of inertia I equals 1/2 mr squared. You are then given that the mass is allowed to fall a distance of 10 meters. Mass is allowed to fall a distance of 10 meters. From there, you must derive what the angular velocity of the wheel is. So we have what we know, and we know what we want to solve for, okay? We're given moment of inertia, and we're given the distance through which mass m falls. We're not given a lot of information, but we can still work with it, okay? So if we have a mass m falling through a distance, that should immediately set off alarm bells in your head saying that we're dealing with gravitational potential energy, equal to mass times g times the change in height, wherein we're dealing with mass m, gravitational constant g, and a change in height of 10 meters, okay? So we're dealing with 10 mg of gravitational potential energy being expended in the system, okay? So we know that 10 mg of gravitational potential energy was consumed. There's no more gravitational potential energy for us to work with, so it has to have gone somewhere. Now, what kids will wrongfully do from this point is they say, oh, if 10 mg of gravitational potential energy was expended, it means I must now have 10 mg of rotational kinetic energy. You would be correct in saying that some of the gravitational potential energy became rotational kinetic energy, but you would not be correct in saying that all of the gravitational potential energy was converted to rotational, because you need to consider that since the mass m is falling, mass m also gains kinetic energy. So the entirety of your gravitational potential energy is converted to the kinetic energy of the block and the rotational kinetic energy of the wheel. All right? Assuming no friction, of course. So let's write that out. 10 mg equals our change in gravitational potential energy equals the kinetic energy of the block plus the kinetic energy of the wheel. 10 mg equals 1/2 mv squared plus 1/2 I omega squared. Okay? So we have the mass of the block, which is known. We have rotational inertia of the wheel, which is known. But we're trying to solve for omega, and we don't know v. So we have two unknowns. What are we going to do? Wait a minute. We have an equation that you need to memorize that isn't given on your reference table that relates v to omega. States that v equals omega r. And we can rewrite that relationship as saying that omega equals v over r. Okay? Then we can rewrite this relationship as 10 mg equals 1/2 the mass of the block times the velocity of the block squared plus 1/2 times the moment of inertia, which is 1/2 times the mass of the wheel. We're going to call that m sub w, times the radius of the wheel squared times omega squared, which we will write as v squared over r squared. Okay? So now I only have one unknown, and that's linear velocity squared. You might be asking yourself why I didn't just convert to everything to omega. The reason for that being is that I am looking for the angular velocity of the wheel, okay? And the angular velocity of the wheel is given in terms of this radius. The angular velocity of the block is given in terms of that radius. So I have differing angular velocities, and they wouldn't be the same, okay? But the linear velocity will be the same because the rate at which the string travels around the circumference is the linear velocity of a point on the circle, and the velocity at which the string is falling is the linear velocity of the mass. So you're going to plug in all of your values, m being the mass of the block, m sub w being the mass of the wheel, and you're going to isolate your linear velocity of the system. And once you have your linear velocity of the system, we're going to use this equation yet again and say that our angular momentum that we're trying, not our angular momentum, our angular velocity that we're trying to solve for is equal to the linear velocity we just calculated divided by the radius of the wheel, v over big R. There you go. Okay guys, that's rotation. Enjoy the AP exam.